purpose of this lesson is to allow you to understand how we use the law of conservation of momentum to analyze one-dimensional collisions. Take a second to look at the learner outcomes for this lesson. You can feel free to pause the video at any moment, or at the end of the lesson, come back and ensure that the outcomes have been met. So in words, the law of conservation of momentum simply says that momentum can be moved within a system from one object to another, but if you were to add up all the momentum before, compare it to all the momentum after an event, then the total momentum should remain the same. Let's take a look using this basic example which we've seen in class. We have a red object with a velocity v about to collide with a blue object with the same mass. After the collision, one possible outcome would be that the red object ends up with a velocity equal to 0, and the blue object moves off with the same velocity that the red object had initially. In this case, you can see that the momentum of the red object before the collision, P, is equal to m times v, and the momentum after the collision of the blue object, P, is equal to mv. I'll use the symbol prime after the v to say that it's the velocity after the collision. So, assuming that the masses are the same between the red object and the blue object, you can see that the momentum of the red object before the collision is the same as the momentum of the blue object after the collision. The sum of all the momentum of the red and blue object before the collision is the same as the sum of the momentums of the red and blue objects after the collision. Now, before we get into any numbers, I just want to point out that there are two possible kinds of collisions that we study in Physics 30. One being elastic. In an elastic collision, both momentum and kinetic energy are conserved. In an inelastic collision, only momentum is conserved. Seeing that in both types of collision, it's the momentum that we can for sure assume is conserved before and after collisions, it's always safest to use the law of conservation of momentum to analyze any collision. We'll see how we can use the kinetic energy conservation law in elastic collisions later on. Let's use a couple of basic examples to demonstrate the difference between an elastic collision and an inelastic collision. Let's begin with two objects, a blue cart and a red cart. The blue cart has a momentum of 10 kilograms times meters per second to the right. The red cart has the same momentum but to the left. Let's imagine that the carts have really good bumpers or maybe magnetic bumpers such as the carts that we use in class, so that when they hit, they have a collision in which there's very little loss of energy or maybe even no loss of energy, so that there's no distortion of bumpers, there's no heat being generated. All the energy that we have in the carts at the beginning and at the end are the same. If that's the case, and our two carts hit and their really springy bumpers do their job, then we could expect that the momentum of each cart is basically exchanged. The blue cart now, following the collision, has a momentum to the left of 10 kilogram meters per second. The red car has a momentum of 10 kilogram meters per second to the right. If we compare the momentums of the system before and after the collision, the total momentum before the collision between the blue cart and the red cart would be 10 kilograms times meters per second to the right because of the blue cart, and 10 kilograms meters per second to the left because of the red cart, for a total of 0 total momentum in the system. As you can see, after the collision, we have the same total momentum. The blue cart has its 10 kilogram meters per second to the left, that would be negative 10 kilogram meters per second, added to the red's momentum after the collision, plus 10 kilogram meters per second, for a total of 0 units of momentum after the collision. So in an elastic collision, the sum of the momentum before is equal to the sum of the momentum after. The total momentum before the collision and the total momentum after the collision have got to be the same. Notice as well that the kinetic energy will be conserved. Imagine that each object has a mass of, well, let's say 10 kilograms to make life easier. If the momentum of object B is 10 kilograms per second and its mass is 10 kilograms, then the velocity of the blue object before the collision is 1 meter per second. Likewise, if the mass of the red object is also 10 kilograms, then its momentum of 10 kilograms meters per second means that it had a velocity for the collision of 1 meter per second to the left. The total kinetic energy of each of these objects then, given by the equation EK is equal to 1/2 mv squared, means that the blue object has a total kinetic energy of 1/2 10 kilograms times 1 meter per second squared. So that means the total kinetic energy of the blue object before the collision of 5 joules. Since the red object has the same mass and the same velocity, then it also has a total kinetic energy of 5 joules. Now, energy is a scalar, so the direction doesn't matter. So the total energy before the collision, pardon me, is 10 joules of kinetic energy. You can see then that after the collision, since the objects have the same velocities but in the opposite direction, you can do the math for yourself and see that the kinetic energy of the red object will be 5 joules. The kinetic energy of the blue object will be 5 joules. So in addition to the total momentum before the collision and after the collision being the same, when it comes to elastic collisions, the kinetic energy is also conserved. In this case, 10 joules of kinetic energy before the collision, 10 joules of kinetic energy after the collision. Now, how is that different than in inelastic collision? Well, in an inelastic collision, we'll use the same numbers as before. Remember, we had our blue object with its 10 kilograms times meters per second worth of momentum before the collision and 5 joules of energy. We had our red object with 10 kilogram meters per second to the left and its 5 joules of kinetic energy. In an inelastic collision, I guess the most extreme example would be the case where two objects actually hit and stick. In class, we'll demonstrate that using Velcro bumpers. But in real life, that's pretty true that if you have a collision between, let's say, two cars at an intersection, when they hit, the bumpers will quite often distort themselves and the cars will kind of stick together after the collision. So in an inelastic collision, or a hit and stick type of collision, the two objects, as you see here, have come together and they're now stuck. If we apply the law of conservation of momentum, remember, our total momentum before the collision, because of the 10 kilograms that's positive, the blue, or sorry, 10 kilogram meter per second due to the blue object's momentum, the negative 10 kilograms meters per second because of the red object, we have a total of 0 units of momentum before the collision. The total kinetic energy before the collision is 10 joules, 5 joules because of the blue and 5 joules because of the red. Let's take a look and see. Remember, the law of conservation of momentum says that after the collision, we should have a total momentum equal to 0. The reason that is because after the collision, if both these objects have the same velocity and same mass and they hit and stick, the velocity of the blue object after the collision is going to be 0 meters per second. the velocity of the red object after the collision is going to be 0 meters per second. So you can see that both objects have no momentum after the collision. Therefore, the total momentum, 0 because of the blue, 0 because of the red, the total momentum is 0. How about the kinetic energy? Well, if the velocities are 0, then the kinetic energy of each object is now 0. They have no kinetic energy. Now, the energy has been converted to some other form, maybe heat in the bumpers, maybe some sound, maybe other forms of energy that have been lost from the system. At any rate, the carts themselves have no kinetic energy. So, if we add up the kinetic energy of both objects, the total kinetic energy of both objects after the collision is 0 joules. So you can see where in the elastic collision, both momentum and kinetic energy can be conserved, but in an inelastic collision, only momentum is conserved. As we go forward with analysis of, or more mathematical analysis of these one-dimensional collisions, we're going to keep those two facts in mind.